enjoyed either last week relaxing or being at the conference. We're now obviously back in the real flow of things. So just a couple of announcements. First is, as I'm sure you guys all know very well, homework number 3 will be due this Friday. So hopefully you guys have already sort of made good progress on that. There was one problem number 2, which, as I said, would really sort of officially finish covering all the material for that basically today. But nonetheless, pretty much everything else on there I think you guys should be more than capable of handling. So hopefully you should have plenty of time to get that all done. The other thing, which is more of a reminder than anything else, is that actually we will be having a midterm fairly soon. So that's essentially about 9 days from today. So not Thursday of this week, but the following Thursday. That'll probably be in the evening. We'll sort of send out more details as to exactly location, time, etc. But I believe I'm tentatively scheduling that for something like 6:30 to 8, something like that. Again, we'll definitely let you guys know once we finalize it. In terms of material, that midterm will cover basically everything up to lecture notes number 10, which I've handed out today, and we'll finish either today or at latest sort of at the beginning of next lecture this Thursday. And then the other thing that I'll just briefly mention is I will do a review session for the midterm. For those of you who've taken class with me before, you'll sort of know that this is the same standard procedure where I will prepare exactly 0 material, but I will come and I'll answer basically whatever questions you have, other than these sort of obvious questions of which question is actually on the midterm and what's the answers and stuff like that. But anything else is basically fair game. So we'll sort of do the scheduling for that this coming Thursday. I'll sort of just take a brief informal poll in class. But we'll probably do it somewhere here, probably in 550 Corey, or perhaps even in this room, probably like in a late afternoon, early evening kind of time slot to try and maximize the number of people that can actually make it. So with that, any questions either on homework, material, logistics, anything like that? Okay, if not, let's actually go ahead and dive back into the lecture notes themselves. So last time we were basically talking about amplifiers in general, and we started talking about specifically how we want to use actually operational transconductance amplifiers, or OTAs, rather than op-amps, because particularly in CMOS, that's typically what you're going to get when you build an amplifier in any case. And then furthermore, we started talking about how we'd probably actually want to be using capacitors for our feedback rather than resistors. And then I think where we basically ended up was this sort of slide right here, which was basically saying that if we were going to use capacitive feedback, well, obviously there was this issue of just initially any node that doesn't have some sort of DC path to a known potential is an issue, because who knows where that node actually ends up at the end of the day. So we said, well, okay, we can go and just add some switch in to try and reset the potential in that node. And potentially you could try and do this once at like the beginning of time or the beginning of operation. But we said that actually has a lot of issues associated with it, with just every time you turn that switch off, it typically has some errors in it. And if you don't really do this often enough, then basically, again, you can run into the same problem of just charge or whatever can leak onto that node and cause things to go bonkers. So at the end of the day, we actually said that typically the way we really do this is we'll do this so-called reset every single cycle. And the advantage of doing that is that if there is any sort of error created by it, at least if we do it every single cycle, it'll show up at the output every single cycle. And therefore, it'll look just sort of like a DC or a constant error term, rather than something that really is moving around with a signal or has some frequency dynamics in it. Okay? So if we really sort of take that idea to the next step, we can build this so-called switched capacitor gain stage that I'm showing you here. Now, I'll walk through in more detail sort of what exactly the circuit is doing in the next slide. But basically, all of the switches that I'm adding here really only serve one of 2 functions. Either they're essentially resetting some node to a known potential, which is, again, that issue that we talked about before, or they're basically trying to configure the circuit into some particular topology to create a desired effect at the end of the day. Okay? Now, I will mention there are lots and lots of different types of switch capacitor, even gain stages, let alone sort of switch capacitor circuits in general. So I'm not going to obviously walk through each and every single one of them, but I will walk through this one specific example here, just because it does turn out to be a fairly sort of simple and effective way of doing things. Okay? The only other thing that I want to briefly mention before we really walk through exactly how this circuit works, and by the way, one thing I'll mention is that with almost all of these circuits, the easiest way to understand how they really operate is just to sort of draw the circuit in each topology and kind of ignore what the switches, what the what all of the other switches that are not on in that particular phase, because they usually just sort of confuse the picture. Again, we'll do that in one more second. But before we do that, I did want to mention one important point, which is that you'll notice I sort of labeled that there's two independent clocks here. So there's a phi 1 and a phi 2. Okay? So you do specifically need those two different clocks, because in particular, if you look at sort of how those are usually set up, if we sort of look at the waveforms very carefully, they'll typically look something like the following. Okay? So in particular, if you notice here, I've made them so that they're so-called non-overlapping, meaning that when phi 1 is high, you're guaranteed that phi 2 is low, and vice versa. Okay? So anybody have an idea why that's sort of a very important thing to do in many of these switch capacitor kind of circuits? Why is it typically really important for you to have these two clock phases, which obviously, by the way, drive the switches, be non-overlapping like this? Yeah, okay. So depending upon which two switches it is, you could indeed basically lose some amount of charge that's related to sort of how much they were overlapping with each other. In fact, it can turn out to be even worse than that, because just as an example in this particular circuit, if you notice if phi 1 and phi 2 are both on, you're just going to be shorting the input to ground. Generally, that's not such a great idea. Although, maybe not the end of the world, but generally not great. Although, as you also actually mentioned, if, for example, phi 1 and phi 2 are both on, you'd also be shorting that capacitor, right? And depending upon how long that thing was shorted, you may actually lose the voltage signal you were trying to sample on that capacitor in the first place. Okay? So it turns out that that sort of non-overlap period there, obviously it's very important from a functionality standpoint. But it actually has some implications on other aspects that you might care about in these amplifiers as well. So just to give you, just to maybe make that point more clear, let's say that I told you that in order to make sure things worked, I needed 1 nanosecond of non-overlap. What does that sort of imply about how I can use this amplifier? What limitation would that sort of impose on us? Yeah, this would basically say there's only so fast we can actually switch this thing, because if I have to have both switches basically off for a nanosecond, then that basically says that obviously there's no way in heck I can switch this faster than a gigahertz, in fact even actually 2 gigahertz. But beyond that, it would actually say that it's probably pretty inefficient to even try to do that, right? Because if my non-overlap power period is a very big portion of my overall operation, that would basically say I'd have to spend a lot of power in my amplifier just to basically get things to settle out during the time I actually am getting the real signals I want. Okay. Now, by the way, this 1 nanosecond here, that's just a totally bogus number. I just made that up out of nowhere. But the point is indeed that you want to make that non-overlap kind of as small as you can relative to the overall period. Because if it's too large, it will indeed cause sort of a large overhead in terms of your operation. Yes? Okay. So you asked the question of what's the reasonable percentage of sort of that overall clock time. The short answer is it really depends. Okay. So, or really to say it another way, and maybe I'll actually turn around the question on you guys. What would you want to make this non-overlap period ideally? Like if you didn't have to worry, life was beautiful, you can control everything perfectly, what would you make that non-overlap period? 0, right? That's exactly what you'd like to do. Now, why can't you do that? What's the sort of, what stops you from doing it? Okay, there's finite rise and fall times. What else? Okay, yeah, there's jitter. Anything else? Okay, jitter and skew, those are, well, let me maybe ask it a slightly different way. That's absolutely correct. But what's causing, for example, the skew in the first place? Interconnect. That's possible, but let me do something. Let's say I did a really good job, and I followed everything that we've learned. Let's say in this class, or perhaps even in 141 or something like that. And this is something like, well, okay, this doesn't exactly work, but let's say that these were my original phi 1 and my original phi 2, and I made those two buffers, nominally exactly the same. Are they really exactly the same? Yeah, okay, there's going to be mismatch, right? You're never going to have those things to be exactly perfectly the same, right? So really at the end of the day, the non-overlap you're going to choose is very directly set by how much mismatch is there going to be in your paths, right? Now, there could indeed be some deterministic mismatch, meaning that, just as an example, you had an extra buffer on one side versus the other, right? And by the way, sometimes you'd need that just because of inversion or something like that. But that's really the bottom line is you're going to make that as small as you can while still guaranteeing that you don't actually have any overlap, okay? And obviously, the less variation you can get in generating those clocks in the first place, the smaller you can make the overlap. Does this make sense to everybody? Or? Okay, so in that case, let's actually go ahead and walk through, a more complete sort of, or more, let's say, a more simple way of actually seeing how this circuit really operates. Okay? And again, as I said before, the way I'm going to do this is really to split the operation into essentially the two different phases. So if you walk through that diagram that I'd shown earlier, in phase 1, what you're basically doing is sort of the picture that I'm showing up over here on the top. Okay? And in particular, you can kind of see what we're essentially doing is sampling the input, or really just making the input drive this input capacitor CS, right? So that at the very end of this phase, if you sort of let go of the switch at the input, there should be a voltage of VI stored across that capacitor CS. Okay? So hopefully that's fairly straightforward or fairly obvious. But there's another sort of interesting thing that I want to point out over here. So if you notice in the OTA, obviously I have ground at one of the terminals. That's true sort of in all the phases. I've also grounded the second terminal there. But in fact, if you'll notice, I in fact even also grounded the output. Okay? So let me first maybe ask a question as to why am I grounding the output like this? Why is that an important thing to do? Or to say it maybe in another way, what would happen if I didn't ground that output? Oh, okay. So you said that if I have some offset, I would actually be pushing some current in that capacitor. That's actually correct. Let's even assume that I don't have an offset. I still claim something bad would happen, or at least bad in the context of what I'm trying to build right now. Give you guys a little bit of a hint. Oh. Okay, and what would that voltage be related to? Okay, so you said that if I don't ground this terminal right here, there'll be a voltage at the output of the amplifier. And you said that it's related to the gain of the amplifier. So I agree with the first statement. I agree that indeed there will be a voltage at the output. But again, if there's no offset, then if I ground both inputs of the OTA, then I shouldn't really be driving any current into the output, right? But okay, so now what's the problem? So you said the voltage and the output will remain the same. So in particular, since I'm trying to build this, why is it bad that the voltage on the output remains the same? I'll give you guys a hint. What would you call, back in probably when you first, E40 or whatever your first sort of EE class was where you talked about op amps. If I give you a circuit that looked like this, what would you say was sort of the transfer function from the input to the output? What was the sort of type of circuit that you were building there? Yeah, it's an integrator, right? Okay, so now we'll return to the question here. If I've got a voltage hanging out at the output of my OTA here, and I'm not doing anything to change it, what kind of circuit do I have? Yeah, it's an integrator, right? What's actually going to happen is that every single cycle you're going to pile up some amount of charge over there. But obviously, unless you do something to get rid of it, it's just going to stick around, right? So that means that indeed, if you didn't actually reset this output here, you'd be accumulating charge on this feedback cap, and indeed you'd be basically building an integrator. Now, by the way, sometimes you do want to build an integrator, but in this particular case, as I boxed up on the top, I wanted a gain stage, meaning I didn't want any memory, right? I wanted to get rid of any previous effect from my previous inputs, okay? So because of that, indeed, I have to basically get rid of the charge on that cap there, okay? Now, let me ask you guys another question, which is you'll notice I sort of highlighted that output sort of node, or that output connection to ground in a different color there. So, if I was to take this this op-amp circuit, which was your original integrator, and I was just tie the output to ground like that. And of course, I'll tie the input over here to ground too. But if I was to just tie the output to ground directly, is that a good thing to do or is that a bad thing to do? And I'm asking specifically on, this op-amp based circuit here. Yeah, it's bad. It's probably, in fact, really bad. Why is it bad? Yeah, so remember the whole difference between an op-amp and an OTA was that an op-amp has a very low output impedance, right? Ideally, it's a voltage source output impedance. So tying a voltage source to ground generally is bad news, right? Because that means you're just going to have essentially infinite amounts of current flowing through that connection to ground, which generally is bad news. Usually something explodes at that point, right? Okay, so now next question is, well, notice I have an OTA here. So is it okay for me to do this? Is it okay for me to just drive this? By the way, when I say ground here, it doesn't necessarily have to be really ground. It could be some other potential. But is this okay? Or is this also bad news? What do you guys think? Okay, so it should indeed be high output impedance. You said you shouldn't have any current. It's true, at least to zero order, there shouldn't be any, let's say, and this is going to be an abusive terminology, there shouldn't be any, let's say, change in the current versus the nominal bias point. But let's actually even draw this more specifically. So let's say I built my OTA sort of the standard way I know how to do in CMOS, and I did something like that. Right? So this is, of course, my input voltage, and that's my output voltage. Okay? And let's say I took this drawing literally, and I connected this through a switch to ground. So problem, no problem? What do you guys think? Okay, it's true. It's perhaps not the most efficient way of doing things. But will anything, let's say, necessarily explode? No, right? Because I've got a current source here, right? So it's true, ideally speaking, I probably don't want to just dump that current source to ground. But hey, I was building an amplifier that was always dissipating that current anyways, right? So just having it go directly to ground through the switch versus go to ground through the transistor, probably not all that different, right? And as long as, of course, I size the switch such that it can handle the current of the OTA, again, that's probably an okay thing to do, okay? So again, this is a little bit subtle, but if you do indeed have an OTA, generally speaking, it is okay to sort of reset its output through a voltage source. Now, there are actually obviously clever tricks you can play where if you instead of grounded this, for example, you drove it to VDD and you grounded the input over there, you could actually maybe make the current go away. But that usually is not what you want to do simply because that then forces the currents to turn on and off sort of dynamically. That involves extra sort of settling of various time constants. Usually that's not sort of how you'll do things. And by the way, of course, the details as to how exactly this circuit is really built has a big impact on what you'd really, whether you'd really ground it or send it to some other voltage or something like that. But the point is indeed that if you really are dealing with an OTA, typically shorting the output to a voltage source is not the end of the world because there'll just be some finite current that will flow due to the OTA. Okay, so to really get back to the sort of main operation of this thing, as you'll see, again, in that first phase, we basically sample the input voltage, or we really drive that input voltage onto this capacitor, okay? And we just reset everything at the output. And then in the second phase, really all we do is essentially disconnect that input, drive this terminal of the capacitor to ground, and then connect that capacitor through the feedback onto the OTA, okay? So to kind of understand how this works, it's a little bit useful to think about sort of what was the initial charge and what happens to that charge when we sort of play around with things like this, okay? So how much charge am I actually storing across the capacitor in this first phase? Yeah, so the charge there is just going to be CS times VI, okay? Now, when you first basically turn on that switch right there and connect, the the capacitor sort of onto the OTA right there. What is the capacitor, or rather, no, maybe I'll make this a little bit easier. So let's assume that I first just closed this switch right here, and I basically let go of the switch right there, and I just measured the potential here relative to ground. What would that voltage be? Yeah, it'd be negative VI, right? Because the capacitor, the voltage can't change because there's no charge flowing through it. So if you used to have a VI across it, then you still have to have VI across it. And now you just moved one side to be ground. So now it's going to be negative VI there. Okay? Well, what happens when I turn on that switch? Am I still going to allow myself to have negative VI sort of at that point right there? Or is something else going to happen? Okay, there might indeed be some sort of charge sharing, but let's not even worry about CF precisely for a second. Let's just sort of look at everything to the right over here and sort of ask ourselves again, back in a sort of classic, let's say, first order circuits class, when we had a node that was like this with an op amp and there was feedback there, what did we typically call that node? Yeah, it's a virtual ground, right? So if that's a virtual ground, then when you connect that capacitor, the OTA is going to do whatever it has to do to keep that node actually at ground, right? Well, so now you guys tell me, what does the OTA have to do to basically keep this node at ground, even though this capacitor wants to push it to be negative VI? Yeah, exactly. It just has to flow some current out of the output and into CF, such that the charge that would have been there basically gets compensated and causes this to actually go to ground, right? Well, okay, so notice we said the charge was just CS times VI. So that means that, of course, the charge we need here is also CS times VI, right? Because that's exactly the charge you need to equalize the voltage across, or rather really to zero out the voltage across the CS capacitor there. Okay? Well, okay, so if that's the case, then what is actually my output voltage as a function of the input voltage? And by the way, we know that this is eventually going to end up at ground. So what's the output voltage going to be? Yeah, exactly. Right? It's just going to be CS over CF. And by the way, of course, the way to get there is just to say that V out is just CS times VI over CF. Okay? It's just the charge divided by the capacitance. Okay? Now, by the way, I did not make any mistakes with the sign here. This really is a positive gain, even though we connected it in a negative feedback configuration, simply because notice between phase 1 and phase 2, I flipped basically the polarity of the voltage on the input cap, right? And so because of that, you indeed get positive gain from this whole structure. There are other topologies that will give you negative gain, so again, user beware. But in this particular case, it really is a positive gain through the whole thing. Okay? Does this make sense to everybody? Or? All right, so just to make sure this is 100% clear, I just want to sort of draw a simple picture that kind of gives us an idea of what the waveforms coming out of this kind of switch capacitor gain stage would look like. Okay? So let's just say as an example that the input voltage is a sinusoid. Oops, let me do it a little bit. Is a sinusoid that looks something like this. Okay? Where this here is 0 volts. Okay? And let's say that my clock, in particular, let's call it phi 1. And let's not worry too much about the sort of non-overlap now. Let's say my clock looks, say, something like this. Okay? So just as a reminder, when phi 1 is high, the output should just be grounded. Okay? So let's actually, and by the way, I'm going to draw that in a different color. Let's do this in blue. So this is going to be my V out. Okay? So when phi 1 is high, my output should basically just be 0 volts. Okay? And 0 volts here, by the way, you shouldn't take it literally, but it's around, obviously, some bias point. Okay? Okay, well, when the clock here goes low, which for now, let's just assume that very, very shortly thereafter, phi 2 would go high, right? That's basically when you're sampling the input, right? So that would basically say that if, for example, my input got captured right there, then the output of my sort of switch capacitor gain stage, and let's assume for now just to make a gain of 1 to make my life easy, eventually it should indeed go to that point. Okay? Now, by the way, will it just immediately jump up to that, or what will the waveform actually look like in order for before the output actually gets there? Yeah, there'll be some exponential settling and perhaps even some more complicated exponential settling if you have, with multiple exponentials, if you have multiple poles and zeros. But basically, you'll have some kind of settling that should indeed end up at that sample point right there. Okay? All right, now, of course, when the clock goes high again, you'll also come back to ground, right? And by the way, that settling may be actually faster or slower than the original settling was, depending upon the resistance of the switches. And then, of course, again, when you sample the input, the output will settle and jump up and eventually get to close to what that value is supposed to be. Then, of course, it'll get reset again. Then you'll sample the input again. It'll come down, right? Then it'll get reset, and so on and so forth. Okay? Now, by the way, my drawing here is not the best one because the time constants should be fairly similar in all of them. But the real point here is indeed that if you look at this sort of type of switch capacitor amplifier, it's obviously only during these samples that you actually, well, in fact, during here, here, and there, that you're really getting the sort of final information that you wanted. Okay? So as we'll talk a lot more about later, in these types of designs, typically what you really are sort of designing for is, given that there's a certain clock frequency here, you're going to design it such that this waveform settles to within some given level of accuracy. So that by the time you use it at the very end over there, you know it's very close to the final target value. Okay? And as we'll see, that actually has direct implications on essentially the bandwidth, the gain, and so on and so forth of the amplifier. Yes? So are you asking, so the question was, why does the sort of voltage across capacitor not track VI? Was that the question? Okay, so if you look at the picture here, notice in this first phase, if I'm looking at the output, I've grounded it. Oh, right? I'm grounding the capacitor. Oh, okay. Oh, right. Right? So basically during half of the time, for all intents and purposes, I should have no output. And only during the second phase, once I've settled, then I will actually get something that's related to VI. I'm plotting V out, exactly. I'm not plotting the voltage across the capacitor, I'm plotting V out. By the way, it turns out even the voltage across this capacitor, in this particular case, if I looked at the voltage across CS, it would also actually have this waveform where it would track VI and then go to 0. Because notice in this phase, if this is really a virtual ground, I will actually zero out the voltage on this capacitor. Right, so that is indeed, even there, that would actually happen. Okay? Other questions on this? Or? Okay. So, now that we kind of understand this, it's a little bit interesting to go back and take another look at our earlier discussion about op-amps versus OTAs. Okay? And in particular, what I'm going to try and sort of explain a little bit now is why you'd actually really want to use an OTA for these switch capacitor circuits. And it's going to turn out it's not just because OTAs are really typically what are easy for us to build. It's actually going to turn out that if we used an op-amp, pretty much everything will get worse. Okay? So in order to understand why that is, again, let's sort of think a little bit more carefully about what an op-amp really is. Okay? It turns out that it's really easy to understand what an op-amp really is by thinking a little bit about the difference between the symbol for an op-amp and the symbol for an OTA. Okay? So notice an OTA is kind of like an op-amp with like its head cut off, right? Like we got rid of that sort of second triangle piece on the second side. Okay? Well, turns out if you were to really build an op-amp, which is a reminder, of course, the only difference is that it should have a low output impedance, what you would typically do is indeed build an OTA and then just feed its output to a buffer, right? As an example, to a source follower to get a low output impedance. Okay? Does this make sense to everybody? Or? Okay, so clearly if we're going to do something like this, then actually we're going to have to spend extra power versus sort of an equivalent OTA, just because we have to add that buffer in, right, to get the low output impedance. Okay? So as I'm going to show you in 1 second, if you really were to do this and use it in a switch capacitor circuit, at least in many of the contexts that we're talking about, you will actually spend extra power to get worse noise than you used to have. Okay? So to see how that would happen, let's just look at the following very simple example. Let's just start first with sort of the OTA side of things. Okay? So let's indeed assume that I have my OTA, which I've basically tied into unity gain negative feedback, because let's just presume that indeed what I want is a gain of 1. And I use that to drive my load capacitor on the other side. Okay? Well, if you think about the OTA, or just a generic sort of transistor-based amplifier, let's assume it's a simple common source kind of thing. Then as we talked about before, if we wanted to input refer the noise coming from that OTA onto the input, you just end up with something like a density, or actually a thermal noise voltage of 4 kT over GM times delta F. Okay, there's a gamma factor here that I'm neglecting, but don't worry about that. Okay? Well, as we had also talked about, I believe last time, if I sort of look at the equivalent output impedance, looking back there, hey, I've just got a GM and negative unity gain feedback, right? So in other words, that output impedance is just going to be 1 over GM. Okay? Well, if you think about it, this sort of whole model here looks exactly like the noise model or the noise calculation we had done for the simple RC circuit, right? Because we have a resistance of 1 over GM, and the thermal noise associated with that resistance is also proportional to 1 over GM, right? So at the end of the day, if I integrated the output noise on that capacitor at every sample point, you'd basically just get KT over CL, right? As we saw several times already. Well, now let's contrast that with a case where I actually use an op-amp. Okay? So here in the op-amp, if I input refer the noise from this OTA, that's still basically just going to be 4 KT over GM delta F. Okay? And in fact, I'm even going to be really nice to the op-amp, and I'm going to assume that this buffer here adds no noise whatsoever. Okay? I'm actually just going to look at the net noise of this whole structure, even with a perfect buffer from the standpoint of noise. Okay? So again, I've got my input referred voltage noise due to the OTA. But now, instead of looking back, instead of seeing 1 over GM, right, what I'm actually going to see is some output impedance due to that buffer, right? Plus, of course, whatever the negative feedback actually does. So I'm just going to capture that as being an RS, some source impedance. Okay? So if we take this model and we again go back and do our very simple sort of first order integrals, right? What you're going to get is not going to be very surprising, right? You're going to have this 4 KT over GM. Then because I have this RS driving the CL, now the integral of that will be 1 over 4 RS times CL. Okay? So now I'm just going to define one thing very quickly to sort of, make the final point clear. Like we had done a couple times in the past, I'm going to say that this OTA has some equivalent noise resistance, which by definition I'm just going to say is 1 over GM. Okay? And what I mean by that is just what is the equivalent resistor that would generate the same input referred thermal noise or thermal noise density as the OTA does. Okay? So if I define the noise resistance as being 1 over GM, then notice I'm still, of course, going to get KT over C, but it's going to be multiplied by that noise resistance divided by the source resistance. Okay? I claim this is actually really, really bad news for the op-amp. So why do I say that that's bad news? What's the sort of key thing to realize here? Yeah, exactly. The whole point of doing this in the first place was that I wanted RS to be small in comparison to my 1 over GM, right? Because otherwise, why the heck did I bother? Like, there's no point, right? Well, indeed, if you make that RS small compared to the 1 over GM, notice you're going to be multiplying the thermal noise that you get, okay? And in fact, if let's say RS is, 10 times smaller, you're now going to have 10 times the thermal noise, at least in terms of a variance standpoint. Okay? That's bad news, right? Because notice I spent extra power on that buffer. I didn't even include any noise from that buffer. and I'm getting way worse thermal noise than I had in the first place. Okay? So it turns out that specifically when you're talking about driving sort of capacitors like this, indeed, you really do not want an op amp. Okay? And by the way, the other sort of way of understanding this is that when you added this buffer in this particular context, all you were really doing was expanding the bandwidth of your circuit, right? And if at the end of the day, I've designed my circuit so that, I'm exactly just meeting the settling requirements, expanding the bandwidth so that I settle even faster really is pretty bad, right? Because all that's going to happen is I'm going to settle more precisely than I even cared about, but I'm actually going to add a lot more thermal noise into the system, okay? So it turns out back when people sort of first started building switch capacitor circuits, they really started using op amps. And then you can go back in the literature and you can see all this stuff about, excess noise and, aliasing and all these other things and why, switch capacitor circuits were just really bad news. Well, turns out the problem was not switch capacitor circuits themselves. It was actually just that people were using op amps rather than OTAs, okay? If you use an OTA, then you get back to your sort of classic KT over C, no worse than sort of any other sort of continuous time circuit driving the same equivalent capacitor. Does this make sense to everybody? Or? Okay. So just one final note, which will actually pop up in your homework. I obviously won't give you the answer, but I'll just point out a couple things that you have to keep in mind, which is that when you're doing the calculations for these sort of switch capacitor gain stages from a noise standpoint, you have to be a little bit careful with keeping track of all of the different contributions. Okay? So let's again just sort of draw that switch cap gain stage basically in the first clock phase, okay? Where we're resetting everything. All right, so the OTA itself will look something like this, as we discussed, right? We would reset the output. We'd also reset the input. And then I'm going to explicitly draw a switch here just to make sure the point is clear. Right? Then we would take the input capacitor and basically have something like this, right? That would be CS. And this would be sort of phi 1 driving that switch right there. Okay? So, my question to you guys is the following. When I turn off that phi 1 right there, what's going to happen from a noise standpoint on the capacitor, on the CS in particular? Is there going to be some noise on the capacitor or not? Yeah, there will be, right? Because after all, that switch has some resistance associated with it. And actually, I'll draw this more carefully. There'd be some resistance there. In fact, if we even think more carefully about it, where does that VI even come from in the first place? Well, some other circuit, right? In fact, it could even be some other switch capacitor circuit that's driving that VI in the first place. Okay? So indeed, when you turn off VI, that means you will sample at the minimum KT over CS on that input capacitor from a noise variance standpoint, right? And in fact, if there's some previous stage that has its own noise variance at the output, you'd sample whatever that noise variance actually is. Okay? So keep that in mind. And by the way, there's other places, there's other capacitors where you're actually going to be sampling some noise voltages or noise charge to be more accurate. Because if you don't keep track of that, then obviously when you calculate the final end noise, you'll have some factors that are actually missing. Okay? Because in particular, when I then go into the second stage, and I take that capacitor and I tie it into the negative feedback, right? What's going to happen to that noise voltage you sampled on there? Yeah, it's going to show up at the output, amplified by whatever the gain of that switch capacitor circuit actually is. Okay? So again, keep track of all these things. Pay close attention to all of the different capacitors and what noise voltages may be sampled onto them, or noise charge to be more accurate. Because if you don't keep track of that, indeed, you can miss some fairly substantial effects. Okay? Does this make sense to everybody? Or? Okay, great. So unless there's more questions on that, let's actually go ahead and move forward to the next set of lecture notes. So this is lecture notes number 10, which I just handed out basically today. Okay, so what I'm going to start doing now is that we've talked a lot about sort of these switch capacitor circuits and things like that, but now we can actually start thinking some more about how we're really going to build some of these amplifiers. And in particular, for today, we're going to mostly focus on why you might do, let's say, a single-ended design versus why you might actually do a so-called fully differential OTA design. And then, by the way, the next step we'll take is we'll actually look in more details to, even some more of the trade-offs as to how you'd really build some of these OTAs. In particular, we'll start talking about the so-called folded cascode OTA, which is kind of the workhorse OTA for most of the sort of general purpose applications you might be interested in. Okay? So let's just first start out by thinking about how would we build the sort of absolute simplest OTA we can think of. So you guys tell me, what's like, the very first thing you would put down for a very, very simple OTA? Yeah, some common source, and in particular, some NMOS transistor, right? First thing you do is probably just some NMOS, common source kind of amplifier, right? That's basically your GM stage. And then, of course, you want some current source to bias it with, okay? Now, rather than me just drawing some ideal current source, let's actually do this for real this time. So what would the sort of current source most likely be on top of this thing? Let's, again, go with something simple to keep our life simple for now. What's that? Okay, you could do a resistor. Let's say I really want a current source. Like I really want a very, very high DC gain. Okay? Okay, you said a current mirror, but on this side, that would basically be just a PMOS transistor, right? And indeed, I may bias this with some current mirror kind of circuit. Okay, and now I'm going to be lazy. I'm actually going to give myself indeed some bias current to begin with. Okay? All right, so indeed, this is sort of your very simple, OTA, but there's one sort of minor point of, let's say, annoyance in this particular structure. So in order for this to really work, right, I can't just sort of drive this input here, this input voltage to the OTA to anything I want it to be, right? I actually have to bias it to some nominal point, right? Because if it's not at the right nominal point, then, for example, if I drove this to ground or negative 5 volts or anything like that, the whole transistor, the transistor would be off and it wouldn't actually operate the way I wanted it to, right? And in particular, if I want to get the GM that I wanted, again, I have to bias this thing in some reasonable point, okay? So we'll talk more in 1 second as to, in reality, how you would solve that particular issue. But at least for now, just so that I can kind of characterize this circuit and walk through sort of what the characterization steps would really be, I'm just going to play a little bit of a trick that's really only valid for sort of SPICE, but wouldn't work in the real world. But again, it's a good sort of trick to keep in mind in terms of doing the characterization. So the trick I'm going to play is the following. I'm going to reuse my same bias current. I'm going to feed it into a diode-connected device. And then again, purely from a SPICE standpoint, I'm going to use that diode-connected sort of device to create a nominal voltage. And then off of that nominal voltage, that's what I'll actually sort of feed as the input into the OTA. Okay? And again, the only point of doing this is that now, with this particular setup, if Vin equals 0 volts, that's kind of like my nominal bias point, right? If Vin is a millivolt, I know I'm a millivolt above the bias point, minus a millivolt below, and so on and so forth. Okay? Does this make sense to everybody? Or? Okay, so once I do this, let me maybe ask you guys. If I'm going to go and I'm building an OTA, and I want to basically characterize it meaning, well, maybe really meaning two things. First, that I want to know it really works. And second, that I want to know that it meets all the specs I care about. What do you think is the very first simulation you're going to run? What kind of simulation are you going to run? Yeah, .dc, right? Okay, so there's actually a bunch of reasons why you're going to do that. But it's .dc. It could also be like a .op, right? You're just going to check the bias point or the DC operating condition of this particular amplifier. Now, by the way, when you do that .dc, what's like, immediately after you do that, what's like the very first thing you should check? What's the very first either parameter or set of parameters you should check after you've done that .dc? GM. Okay, yeah, that's not a bad one, although I would go even one step before that. Okay, there we go. The first thing I would actually check is the bias currents. Okay? Why do I say that? Well, because sometimes I make stupid mistakes, right? Sometimes I connect the transistor with, the gate connected to whatever. I just do something really stupid, right? Or let's maybe make another example. Let's say that transistor was supposed to be 1 micron. Well, let's say I messed up somehow. I actually made it 1 meter, right? Well, obviously, life is not going to be so good, okay? So the very first thing you check is indeed just the bias currents, right? And in fact, those are so sort of important that oftentimes it's a good idea for you, even once you've drawn this thing in Cadence or whatever it is, to go and just annotate what do you think the bias current is actually supposed to be here, right? Because when you do the layout, that's important, and obviously for you just checking that the thing is hooked up correctly, again, very, very important, very useful information. Indeed, once you have that, you may also then want to go and annotate what the GMs from the relevant transistors are supposed to be. But, if nothing else, definitely check the bias current, because if it's not quite right, or if it's way off, then clearly everything else you do afterwards is going to be totally busted, right? Now, having said that, obviously none of these current mirrors is going to be perfect, right? The VDSs will always be slightly different, so you're never going to get exactly the mirroring ratio you expected. But at least if they're sort of about right, it'll give you an idea that, indeed you've hooked this thing up kind of the way you wanted to. Things are, roughly speaking, operating where you want them to be. Okay? Make sense to everybody? Okay, so once you've done that, then indeed you'll take that DC simulation. And typically the first thing that I like to look at is just the DC input to output transfer characteristic. And then in 1 second, we'll also draw the sort of small signal gain from that. Okay? So I like to draw this sort of input to output characteristic because this sort of tells you some interesting or useful potential information, right? The first is that obviously just by kind of eyeballing this plot, it should be pretty obvious that there's kind of only a certain range of input voltage swing over which you're likely to get some reasonable gain out of it, right? Because obviously beyond that, you start sort of clipping out and it's not really acting so much as an analog amplifier. It's probably acting more like an inverter in this particular case, okay? Now, the way we typically obviously characterize this a little bit more, let's say accurately or completely, is not necessarily to draw the input to output characteristic, but actually to draw the small signal gain, okay? So I'm going to draw that on this plot as well, but I'm going to do it in a kind of maybe slightly flipped way from what you maybe are used to. So rather than drawing the gain versus the input voltage, I'm actually going to draw the gain versus the output voltage, okay? So the way that would look would be something kind of like this, okay? And, my drawing's maybe not perfect, but as you can kind of see, it's over the same range of input voltage you're actually getting high gain. And then, of course, if you go outside of that, the gain basically drops off. Okay? I just drew it flipped on its side like this because I'm kind of measuring the gain versus output voltage rather than gain versus input voltage. Okay? Make sense to everybody? Or? So, as we've talked about several times before, you would take this plot and you could basically immediately use it to say, well, okay, let's say I had a certain gain specification, right? Let's say I wanted a gain of, I don't know, let me just draw some arbitrary line over here. Let's say I wanted a gain of at least 20, right? Well, I could now then take that plot and say, well, if I want a gain of at least 20, then that means my output voltage swing is constrained within that range right there, whatever that range happens to be. Okay? All right, so that's fairly straightforward, but actually it turns out we've been lying a little bit when I've been talking about gain so far. Okay? Because in particular, what I plotted here was the small signal gain, meaning the derivative of the output voltage with respect to the input voltage. Turns out that may or may not be actually exactly what you care about. Okay? So in particular, to sort of make that point hopefully clear, I'm just going to redraw that plot on this picture right here. But I'm actually going to compare it against the so-called large signal gain. Okay? So let's say that again, I'm going to plot my output signal here. And first, let me plot my small signal gain, which again, I've just defined the standard way, and I've done it with a lowercase a there, as just being the derivative of the output voltage with respect to the input voltage. Okay? And let's just say, as an example, that 0 volts is right here, and as we were showing before, we're going to have some plot that kind of looks like this. Okay? So I'm really just redrawing the previous plot with the axis, flipped here right now. So now let's really ask ourselves the question of whether or not we actually care, and let me just fix this plot a little bit to get it a little bit more symmetric, but it's not super critical. So let me just ask you guys the question as to, do we really actually care about this small signal gain, or might we actually care about something else? So think about that one a little bit, but to really sort of drive you in the right direction, let's think about how we actually will typically use this OTA. So just as an example, let's say we're going to use it in our sort of capacitive feedback configuration, right? So something like this. So we have our input, we have our CS, we have our CF, and that's our output. Okay? So if I have an amplifier and feedback like this, and let's just make up some numbers here. Okay? Let's say that my input voltage over here relative to some, let's just call it the input voltage, absolutely. Let's just say that it's 200 millivolts. Okay? And let's say that I've set this thing up so that CS over CF is 2. What should my output voltage be? What should Vout actually be? And let's not worry about, inversions and things like that for now. Yeah, it should be 400 millivolts. Now, it's never going to be exactly 400 millivolts. Why is that? What's sort of the issue? And now, by the way, I'm actually taking the real OTA that we just built a second ago, and I'm using it in this feedback circuit here. Why is it not going to be exactly 400 millivolts? Okay, you said you're no longer in small signal regime. Let me even ignore that. Let me even assume I was perfectly small signal. Okay, you said there is some range over which the current source will actually stay saturated. Let's even ignore that for a second. Let's assume I indeed had an OTA that, the range was kind of infinite, or at least it's within this range that I've sort of drawn here. What's the other thing that's going to stop you from getting exactly 400 millivolts? You said the gain is nonlinear. I think the gain being nonlinear doesn't fundamentally stop it. Settling time? I'm going to wait forever. There we go. The gain is finite. Right? So remember, every time we say that that node there is a virtual ground, that's only true to within some degree of approximation. And in fact, it's only really absolutely true if the gain was infinite. Okay? Well, the gain is never infinite. Right? It's always some finite number. There's some finite maximum small signal gain we got here. But now here's really the next question. Let's say, indeed, I only got some finite small signal gain out of this amplifier. But now I start actually, indeed, making some very big changes at this input over here. Here's really the key question. If I want to know how close this thing is really to 400 millivolts, do I care more about, for a 1 millivolt change around 200 millivolts, how much the output changes? Or do I actually care about how close, given this entire 200 millivolt input, does the output actually get to 400 millivolts? What do you guys think? The latter, right? Because notice the first question was kind of a silly question. Right? It said, well, okay, if I put in 200 millivolts, and then I went from 200 millivolts to 201 millivolts, the small signal gain would tell you, indeed, how much did the output move due to that 1 millivolt change. But most of the time, that's not actually what you care about. What you actually care about is, given the fact that I put in 200 millivolts in the first place, how close to 400 millivolts will I actually get at the output? Similarly, if I put in 201 millivolts, how close will I get to 402 millivolts at the output? Okay? So it turns out that the question you're typically more interested in is really related to the so-called large signal gain. Okay? And the only distinction I'm making here between these two is that notice in the large signal gain, rather than taking a derivative, I'm actually literally saying how much did the output voltage move relative to the nominal bias point? divided by how much did the input voltage move relative to the nominal bias point. Because I claim that this parameter here, this metric here, is actually telling you in a large signal or in sort of a general sense how much sort of, let's say, change in the output or how much movement in the output are you getting given some movement in the input, right? And again, this is not at some small bias point. It's actually saying if I try and move this thing all the way from 0 to 200 millivolts, how much change in the output will I get to drive that final output to the right point? Okay? Does this make sense to everybody? Or, by the way, maybe just to say it another way, this is kind of like saying that it's the integrated change or the overall change in the output that's mattering rather than the changes at each small individual point. Okay? So just to make sure that this is clear, let me maybe ask you guys another question. So if I looked at this large signal gain, and I was to plot it on this same plot right here, and let's actually maybe take a vote. Who thinks that that large signal gain would be narrower, meaning that it would start to drop off for a smaller range in output voltage than the small signal one does? In other words, it would maybe look something like this. Who thinks the large signal gain looks like that? Raise your hand. Okay. Who thinks the large signal gain would basically look the same as the small signal gain? Raise your hand. Okay, well, there's only one option left. So the only option left is that the large signal gain would look wider, right? It would actually look something, let's say, like this. Who thinks that's correct? Okay, only one brave soul. So I have to fail 90% of the class or something like that. So you have to pick one. Who thinks it's the curve I just drew? Still 1, 2. Okay. Who thinks they look the same? Who thinks it looks narrower? Oh, interesting. Okay, so why would it look narrower? And if your answer is, you had to vote on something and that was the last choice, then that's fine. Then say so. Yeah?
Because as you keep increasing your, from your normal bias point, as you're going farther and farther, the right to the left, the size of that step gets bigger. And so even if you're only increasing by a small amount, you still increase the bottom right.
Okay. So all of the sort of steps that you took were correct. It just turns out that unfortunately the final answer you got was flipped from the real one. Okay? So here's the trick. If we go back and we look at this curve, which is indeed the output versus input curve, what you indeed said was that, okay, well, look, for a small range around here, right, as I move the input, at least initially I'm getting a big change in the output, right? And in fact, within this region here, if this is really just a straight line, there would be no difference whatsoever between this and this, right? Because if it's a straight line, the derivative is indeed exactly this expression, right? So that says that at least in the region where this thing is flat, small signal and large signal have to be the same, right? Now here's really the key question. Once this starts bending over like this, what changes faster? Does the instantaneous slope change faster? Or does the entire change in output divided by the entire change in input change faster? What's that? Yeah, the instantaneous slope can go down much faster than the entire change does, right? Because, for example, let's just draw an ideal inverter, right? An ideal inverter would look like this, right? Notice the slope instantly changed. I would have exactly 0 small signal gain once I passed that point. But the large signal gain would still be just fine, right? Because, okay, maybe I was supposed to get, I don't know, if I was at this point right here, obviously, if I had infinite gain, I would have thought this went off to infinity. Fine, I didn't get infinity. But still, for a very small change in the input, I still had a large change in the output, right? So in other words, it turns out that indeed, this curve always looks like what I've drawn here. It's always wider from a large signal standpoint than it is from a small signal standpoint. By the way, that's actually very good news because it means that if you actually cared about large signal gain, you usually will do better than what the small signal gain would have implied, right? Is this now clear to everybody, or? Okay, so one other sort of interesting question here. I actually kind of intentionally didn't draw anything in the center of that line right there. Just based on sort of how I've defined things, and particularly if you really literally ran this and you plug this into like Spice or MATLAB or something like that, anybody have a guess why I didn't draw what that center point actually looks like? Or what you might actually get when you try and calculate it?
Well, at the very center, you have like division by 0.
Yeah, exactly. At the very center, you'd have something like 0 over 0, right? So depending upon exactly how you set things up, the curve might actually do something like this, or something like this, depending upon what Spice or MATLAB or whatever it was decided to do to you that particular day, right? So the point there, of course, is not that the real large signal gain actually does something ridiculous like that. It really just converges to the small signal gain, kind of by definition of derivative and all that. But just user beware, because indeed, if you try and do literally this calculation in Spice or anything else, you are likely to get behaviors like this if you really push it too close to that nominal bias point. Okay? So just be careful. That's not real. It's not anything to actually be worried about. It's just a mathematical sort of glitch, let's say. Obviously, if you go out into any reasonable region, everything will be just fine. Okay? Okay, so once we've done all those sort of DC characterizations, the next one obviously you do is just a sort of simple AC characterization. And I'm not going to spend a ton of time on this because, again, I think you've seen this a whole bunch of times in the past. As the sort of plot here is indicating, typically you'll get sort of a first order kind of response. You'd use that for all of the standard things that you would use from a feedback standpoint. So let's say phase margin, gain margin, unity gain bandwidth, etc. We'll talk a lot more about how we'll even use this to sort of calculate things about settling and switch capacitor amplifiers. But I do want to just mention one thing very quickly, which is you should remember this plot is only at a single bias point, right? It's only for some given input being fed into your amplifier, right? So in particular, you should perhaps check, especially if you have a fairly sensitive circuit, not just this plot at one particular bias point, let's say at a 0 inputs into your amplifier, but actually across a range of inputs into the amplifier, especially if you're going to be doing something like applying a relatively large signal into it. Because if you have a feedback circuit like this, and indeed there's some big variation in the characteristics of the amplifier as a function of that bias point, then you may find that actually you get very different characteristics, and therefore you may no longer actually be stable. Okay? So just as a simple example, typically speaking, if you change the bias, let's say you went from a 0 volts bias to something like 100 millivolts or something like that, typically your GM would go down, so of course your unity gain bandwidth would move around, and so on and so forth. Okay? So again, key take-home point here is just that don't necessarily look at this at just one bias, but check it in all of the relevant biases that may matter for your particular circuit. Does this make sense? Or? Okay, so once you've done that, the next sort of most relevant thing that you're likely to characterize is the noise performance of your amplifier. And there it's mostly, I shouldn't say characterize, it's mostly to sort of verify that things, again, are working the way you expect them to. Okay? So Spice or Spectre or really any of the other simulators have a couple of very nice features when it comes to noise. In particular, they will not only just tell you what the total noise at the output is, and actually, in fact, integrated over all frequencies, you can actually look at which component in your circuit is contributing to the noise and how much. Okay? So as an example, let's say that we again had our sort of very simple OTA circuit. Let's say something like we had drawn before, so the PMOS current source with the NMOS input. Right, and let's call this M1 and M2. Then indeed in Spice, it will tell you what is the contribution of M1, which in this particular example would be this green curve on the plot right here, as well as what's the contribution of M2, which again in this particular example would maybe be that blue or cyan curve on the plot right here. Okay? Point, of course, here being that when you're building your amplifier, you'd like to know, if indeed I'm getting back a noise that's not what I expected, useful to understand which are the components or which component is really kind of out of whack, is not behaving the way you would expected it to. Okay? The other thing I wanted to just sort of briefly review here, which I hope all of you sort of figured out or realized either from doing homework number 2 or at least from looking at the solutions to homework number 2, is that indeed if you have some amplifier circuit like this, then you're always going to have noise not just due to the input devices themselves, but due to the load devices, due to the current sources, and so on and so forth. Okay? And in particular, if you look at this specific circuit here, it's often easiest to characterize the impact of those extra load devices in terms of the noise performance as just really being relative to the noise you would have gotten from the input stage in the first place. Okay? So if you walk through the sort of derivation that's being done here, the easiest way to do that is just to input refer the noise and then just look at how big the noise due to, for example, GM2 or the current noise of M2 right there is relative to GM1. Okay? So here, again, if you just input refer it, everything is pretty easy. You just get a ratio. Obviously GM1 is just 1, and then you get the GM2 over GM1. And the reason we actually did this in the first place is that for this particular structure, we know that M2 has to have the same current as M1, right? Which means that the ratios of their GMs are really just set directly by the ratios of their V stars. Okay? So at the end of the day, of course, it tells you that what you'd really like to have is as high of a V star for M2 as you can, right? Because the larger that is relative to M1, the sort of smaller the extra noise you'll pick up due to that M2, right? Again, nothing very surprising. This is something we've talked a lot about back when we sort of talked about current sources, okay? The only other thing that I want to mention is this sort of, bracketed thing that I did right here. It's pretty common for people to essentially, for some generic amplifier, not even necessarily this particular OTA I'm drawing here, to basically say that the noise is going to be something like 4 kT gamma times 1 over GM times this NF factor. Okay? So that NF factor there is usually just being used to capture the extra noise density due to all of the other stuff inside of the amplifier besides the main transconductance itself. Okay? So again, you can imagine if you have some more complex circuit, in general, you can typically capture the extra noise density just with this NF factor, which, for anything practical is always going to be greater than 1. Okay? Just one thing that I will note, and unfortunately I will not be perfect about this either, typically when people use this NF factor, they're referring specifically to the noise density and not to the integrated noise. Because the integrated noise, obviously, if you have different nodes in the circuit, can really affect things in a very different way. Typically, this is really for density and not for the integrated noise. Unfortunately, occasionally, people will use this factor even to describe what happens with the integrated noise case as well. But just, user beware. Make sure you understand exactly the context as to how this NF is really being used. Make sense to everybody? Or? Okay, so now let's kind of come back to that initial point where we had set everything up and said that, we were going to build that OTA and we were going to sort of, play that spice trick to actually bias it up. Well, as is hopefully clear by now, especially, typically when you actually build these kind of circuits, you won't actually do the sort of single-ended thing that we had drawn. In fact, what you'll actually do is sort of much closer to what people did, what you did again back in E40 or whatever it was. And I apologize, this should really be an OTA, not an op-amp, right? Rather than using this sort of single-ended kind of structure here, you'll actually use a differential structure like this, okay? Now, if you think about this a little bit more carefully, that's actually kind of a little bit surprising at first. Because if you think about this structure here, you have more devices, right? You actually typically are burning more power for the same transconductance. So in many respects, this sort of structure here is actually a lot worse than that single-ended one, right? From an efficiency and noise and etc. standpoint. Because again, you've just got extra devices that aren't really doing much of anything, except for one thing. So the only reason you would typically use something like this, at least from a zero order, or like, let's say, very lazy standpoint, is that, as we said before, this V-in can't really be anything, right? It really has to be kind of in a reasonable point, or reasonable range, compared to the nominal bias of that transistor. And if it's not in that point, then the OTA just doesn't really behave the way it's supposed to, right? Whereas if I have this kind of differential kind of input, or at least this differential OTA, now I can really reference everything against that other terminal, right? In other words, I know really what this VI is supposed to be compared against. In this particular case, it's referenced against quote-unquote 0 or ground, right? So in other words, I really want this differential input here, largely speaking, just to get rid of kind of systematic offsets. In this particular case, that would have been due to the transistor sort of bias point itself, okay? But if you kind of think about it, that's still not such a great argument, right? Because you're basically saying, well, look, I was really lazy. I didn't want to have to deal with whatever this bias point was, so I'm just going to add this differential input, right? And I'm going to pay extra power, extra noise, and et cetera to do it. Still not such a great argument. Well, turns out the real reason you'd typically want to do this actually has a lot more to do with trying to essentially reject, let's say, interference or let's say, error sources that are not related to your signal, okay? So in particular, the real reason you typically want to do these differential kind of things is actually to basically get what's called common mode rejection, okay? So in particular, let's just sort of think of a specific example. Let's say I go and I build that amplifier circuit and I do my layout and everything, and for whatever reason, there's some wire running nearby my actual feedback node, okay? And let's say that wire capacitively couples me to some other error signal, right? Well, if I indeed have some capacitive coupling like that, then now with this amplifier here, well, guess what's going to happen? If that error signal moves around, it's going to show up at the output, right? In other words, you can't tell the difference between things that are happening on this error signal versus things that are really happening on the actual signal you cared about, right? So specifically, this sort of single-ended amplifier is really just sensitive to any stray coupling or kind of errors you have in the environment around you, okay? Well, so the whole idea with, of course, this differential amplifier is that if I have a good differential amplifier, and I do sort of things in a good way, then if I can make that error signal, rather than just showing up on that node, actually also show up on the other node over here, then at least if that OTA is good, the error will show up on both of those inputs, meaning it'll be common mode. And in principle, the OTA would just reject it. It would ignore it, right? And it wouldn't actually show up at the output. So that's really actually the most important reason to do something like this, is really to buy yourself robustness against all of the other junk that might be in the environment. Okay? Now, having said that, there's still a very sort of, let's say, valid question to be asked here, which is, if I really had a structure like this, so exactly with the whole circuit that I've drawn there, will I actually get the common mode rejection that I wanted? Or is there a little bit of a problem here? And I'll see if somebody else can get it besides Paul. So who thinks, even if I make these two capacitors exactly perfect, will I really get the common mode rejection that I want? No. Why not? Okay, this output's single-ended. That's true. There is some asymmetry that's created by that, although in this particular example, I don't think that's actually the problem. What other problem is there? Yeah, exactly. That's the issue, right? Notice, if I have a parasitic capacitor going into this node versus a parasitic capacitor going into this node, this thing is ground, right? If that's really ground, then I can put whatever capacitance I want there. I'm not going to change that voltage, right? Whereas here, there is indeed some finite impedance, okay? So in other words, because the inputs were asymmetric, actually, I will not get a perfect rejection of that common mode signal. In fact, in this particular case, most likely I won't get any rejection whatsoever, right? Because again, if ground is really ground, I can't really change that relative to the other side. Okay? In other words, the impedance is really very low. Okay? So the real point here is that indeed, if you're going to try and do something like this to actually get that common mode rejection, you have to follow sort of one of the very first rules that we taught you, which is anytime you want two things to match, they have to be exactly the same. Okay? And if you want them to be exactly the same, well, that means you have to build a so-called fully differential circuit. Okay? So what I mean, of course, by fully differential circuit is now I'm not just going to take an input on one side and measure an output on one side. I'm actually going to take a differential input and a differential output. Okay? Because again, I claim that this is really the only possible way for you to actually build circuits such that you would actually get very good common mode rejection. Okay? Because otherwise, there's always going to be some inherent asymmetry in the circuit itself. Okay? So indeed, this is actually the structure we're going to be using throughout most of the rest of the class, or at least generically we're going to be looking mostly at fully differential circuits. Again, to really buy us that extra immunity to all of those common mode kinds of errors. The other advantage, by the way, of using fully differential circuits is that, unlike in the previous case, we're actually not going to pay any real penalty from a power consumption or noise standpoint. Because now, both sides of the circuits are actually being used to give you gain and so on and so forth. Okay? Okay, so having said that, there are really a lot of very, very good properties about these fully differential circuits. But don't ever forget about the common mode. Okay? So just to make sure that that's really clear why I say that, let's just sort of give an example. Okay? So let's say that I'm going to do this whole thing. My OTA is going to run off of a 1.2 volt power supply. Okay? And let's say that just, I don't know, as an example, I'm going to put 500 millivolts on the input plus right there, and 501 millivolts on the input minus there. And by the way, both of those I'm measuring relative to ground. Okay? And let's just say that, just as an example, I gave this a closed loop gain of 1,000. Okay? So if I do that, then indeed, I should get a 1 volt differential signal at that output right there. Okay? So far, everything, at least in principle, is fine. However, if you think about it, there's lots of different ways I can create a 1 volt differential output, but have essentially a very, very different common mode. Right? So just as an example, let's say that I told you that, I don't know, due to some cosmic particle or whatever the heck it may be, and in case you think I'm joking, cosmic particles really are an issue in some of these things. Let's say that from whatever reason, this was actually 10 volts, and this is 9 volts relative to ground. Well, clearly your 1 volt amplifier is not going to be particularly happy with that 10 volts sitting at the output over there. Right? Not really going to work the way we expected it to. Okay? So the real point here is that, again, even though in principle, sort of fully differential circuits buy you a lot of immunity to the common mode, you really can't ignore the common mode. You really have to pay pretty close attention to make sure that that common mode, largely speaking, doesn't go completely out of whack. Okay? So in particular, just to make sure that that's sort of really clear, let me just draw, let me see if I can find some space. Yeah, I'll do it right here. Let me just draw sort of one circuit that happens to pop up in a lot of interviews that people like to give, particularly new graduate students, or in fact even more senior graduate students as well. Okay? So I'm going to draw a very simple circuit here, and all I'm going to do at the end is ask you guys what's wrong with it. Okay? So I have an IB, I have an IB, I have a differential pair, and I have 2 IB down over here. Okay, and I've got my VI plus, VI minus, and of course my differential output over here. Okay, so you guys tell me, and not Jethro, just since you raised your hand too quickly. What's wrong with this circuit? Yeah? Yeah, okay. So you don't, and specifically, you're absolutely right. You said you're not going to know anything about what the output voltage is going to be. What exactly specifically do you mean by that in the context of what we just talked about? There we go. You have no idea what the common mode output voltage is, right? Because if this is really a current source, then it doesn't care what the sort of DC voltage you put across it is. It gives you the same current, right? So indeed, there's actually, well, as I said, this is a very common interview question. There's, in fact, unfortunately, lots of chips that failed because someone didn't quite realize this, or they didn't pass the interview or whatever it was. If this is really a current source, you're saying nothing about what the common mode voltage actually is. And so you really actually cannot build a circuit that looks like this unless you have a way of explicitly controlling what that common mode bias point actually ends up being. Okay? We'll talk a lot more about how you do that. That typically involves doing some kind of so-called common mode feedback. But the long story short is anytime you see a circuit where there's basically just two current sources driving onto a node, better be really careful because you're not actually going to know what the bias point is unless you've done something sort of special to take care of it. Okay? And again, this is a very, very common interview question that, I know PhDs from certain institutions that, didn't quite get it because they just, from whatever reason, didn't learn about this stuff. Okay? Make sense to everybody, or? Yes. So the only point here is that notice if this transistor is really saturated, meaning it actually looks like a current source, then what I've got is one current source and another current source. Well, if I have two current sources, that implicitly means that voltage there can kind of be anything, right? Because that wouldn't change the current whatsoever, right? Well, in reality, you can't actually tolerate anything. There's only certain voltages that really, or there's only a range of voltage that is actually good for what you're trying to do, for actually getting sufficient gain and et cetera out of this circuit. So anytime you have a circuit like this, better make sure you keep track of the common mode. Does that make sense? Or?
So you're basically saying that the output voltage doesn't matter a lot, right?
I'm basically saying that the actual bias point, which is really what the common mode is in this context, does actually matter, right? Because if you just completely ignore it, Murphy's law says that it'll end up somewhere that you didn't want it to be. That's really what it comes down to. All right, great. So unless